All right, class, in this lesson we're going to take a look at section 13.5, binomial experiments, and we're going to take a look at some binomial experiments and take a look at what they are and what they are not. Here we have a coin flip, rolling a die, testing a computer chip, an inoculated person with a flu vaccine, buying a box of cereal, guessing at multiple choice questions. These are all examples at binomial experiments, and the key here is that binomial trials have only two outcomes. So there's a success and there's a failure, and there's not any more options than that. So here the examples of successes and failures is that if you flip a coin, you can either get heads or tails. If you roll the dice, you can get a total of 7 or something other than 7. Now here is a weird example because when you roll 2 dice, you could get, a lot of different options, but the key here is the success is what you would win. So this is kind of like your win versus your loss. So if there is one way to win and one way to lose, then you're still at a binomial. So here we have a computer chip, is that it works or it doesn't work. Talk about whether or not it gets the flu or does not get the flu. So even in a situation like buying a box of cereal, the key here is that you can get a new collectible or one that you already have. So that would be the success or failure there. Obviously, buying a box of cereal does not always turn out to be a binomial experiment, but in this situation where we've got a certain outcome that you're looking for, you either win or lose. And so multiple choice, there's usually 4 options. Or 4 or 5, but the key here is that you either get it right or you got it wrong. So win, loss, or right, wrong, they're still binomial experiments. In fact, here is a list of 4 rules that you have to be looking for to know whether or not it is actually a binomial experiment. So when you're being asked your questions, you're going to be looking through these 4 right here. You might want to take a picture of them and have them waiting there for you, so when you do these problems, you can just quickly shoot through. And so you've got a fixed number of trials that has only 2 outcomes, success or failure, win, loss, whatever. The probability is the same from trial to trial, which means like if you have a 1/4 chance of getting the answer right, it's still 1/4 chance each different trial. And then trials are independent of each other, so it doesn't, when you do one thing, it doesn't affect the outcome of the next particular trial or problem. So here we've got some examples of experiments that are not binomial, and so you roll a single die until a 6 comes up. Well, that's not a binomial because you're rolling different things, and so we shoot through here and we've got trials are independent of each other, so it's kind of falling there. The probability is the same each time, but you've got a fixed number of trials, I think, is the final reason why this is an answer no. Because at first look, it looks fine. You're like, well, I keep losing because I'm not getting a 6, but the experiment has a fixed number of trials. So you're saying, I'm doing it 7 times, so I have to get it, what's the chance of getting it within 7 times or something like that. So here, a student takes a course and earns either A, B, C, D, or F. And here you've got multiple outcomes, although some of us only see an A or maybe a B as being successful, but there are a lot of people that are happy with their D because it gets them to pass. So at different schools, some schools don't accept the D, and so C seems to be the success for a lot of people. So there's multiple outcomes here, so that's why that one fails. And then select 4 cards without replacement and observe whether or not a heart is drawn. And so here you've got 4 cards without replacement, and the trials here have to be independent. And when you don't replace the card, you have a dependent situation where when you take one card out, the next, now you just changed out how many cards there are in your hand, and so that means that they are dependent on whatever you just drew out. So it is not an independent experiment, and that's why C fails. Okay, so here we've got a student taking a 14 multiple choice quiz. What's the probability that a student will answer exactly 7 of the questions correctly by guessing? Assume that each question has 4 options. So this last part is key because it tells us that if there are 4 options, there's only 1 right answer. That means each problem you have a 1/4 probability, or 0.25 is your probability of getting a right answer. Okay, so here we have got a wonderful formula that will do this for us. It probably doesn't look like it's going to make sense yet, but it hopefully will. So your formula for computing binomial probabilities, this is what you're going to be using multiple times in your assignments. And so the key here is knowing what each letter means. We've done combinations before, and that's what this part of this is. So we're doing a combination, and we're multiplying it by a probability to a power, and then you've got 1 minus the probability to the n minus k power. So we just got some formula work, some math work to do here. So the combination formula, well, the n and the k. So let's talk about what those are. It says n is the number of trials. Okay, so here we've got 14 questions. Okay, so that's 14 trials. K is the amount of successes you need. Well, I need exactly 7 successes correctly, so that is my success 7 times. It's my K. And then P is your probability of each individual success. So these are individual successes, which each time you have a quarter chance of getting this right. So the way that this works out is that we're doing the combination of 14, and we need to get 7 of them right. And the probability of each individual trial is 1/4 or 0.25. To the k power, we decided that k is 7 times, so that's this guy right here. And then we have 1 minus our probability is 0.25. To the, our n is 14 minus 7 power. So the key here is just, you can actually just plug this straight away into your calculator, which I will do. Also, a reminder here is that this is our formula for combinations that we had a few lessons ago. So we can actually write that up for us, which here would be n factorial. I'll write it off to the side. So this is n factorial over n minus k factorial times k factorial. And the reason I changed it is because that was n and r in the previous lessons, so it's just, I'll write it that way for you. So it was c n comma r, or p comma r, and anyway, so this is how the formula rewrites with the n and the k. Right. So we can, again, hopefully you have a calculator that will actually do this function for you. If not, you just set it up and work it out the long-handed way, 14 factorial over 14 minus 7 factorial times 7 factorial. Okay, and then I'm going to actually plug the rest of this in my calculator here. So let me pull that up. When I throw it in my calculator, I got 3,432 for this. And again, the calculator shows NCR like that. And so I type in the 14, push this button, and then type in 7, and then push equals, and that's what it gives me when I do it on my calculator. And then I go ahead and type in my 0.25 to the 7th power, and that gives me a very large number. So what I'm going to do is I'm actually going to type this all on my calculator at once. So I do the 3432 times my 0.25 to the 7th power times 1 minus 0.25 is just 0.75. So 0.75 to the 14 minus 7 power, which is just 7, so to the 7th power. And then I go ahead and push equals, and that gives me this whole answer is about 0.02796. Oops, I didn't write on there, did it? So 0.02, I'll round it to 3.8. So 0.028 is your chance of getting this to happen. So in other words, 2.8% chance of you actually getting exactly 7 of the questions correct by guessing. Okay. So we're going to try it a couple times here. We've got a pharmaceutical company claims that a new drug is effective 75% of the time. This is our probability of an individual occurrence happening. So the company, assuming that their claim is accurate, if we test the drug on 20 patients, this is the total amount of people, what is the probability that 15 will benefit? So this is our number of successes. So looking at our formula, we have 20 is the total amount of people, 15 is how many successes I'm looking at, and this is the probability of that occurring. So here the 20 is the N, the 15 is the K, and the probability is 0.75. So if I write it out, we've got C 20, 15, and then your probability is 0.75 to the K power, which is 15, and then times 1 minus 0.75 to the 20 minus 15 power. So just reducing this again, I would throw it in my calculator. In fact, I'm going to. So I've got 20 NCR 15, and that gives me 15,504. So 15,504, and then 0.75 to the 15th power. It's going to be a really small decimal. And then this is 0.25 to the 5th power. So I'm going to go ahead and type all that into my calculator at once. So 0.75 to the 15th power, and then times 0.25 to the 5th power. And that gives me 0.202. And so that's 20.2% chance that you will have exactly 15 people benefiting from this drug. So, and that could be because it's more likely to have actually more of the people, I don't know, overall, but here 15 people will benefit is 20.2% to have exactly only that number happen. Okay, so it'll change. You would have a different answer for exactly 14 versus exactly 16 people benefiting from the drug. We would just do this over and over a few times. Okay, and so here we've got Maria. She fell behind in her anthropology class, and her instructor just announced that a pop quiz consisting of 10 true or false questions, she must get 6 or more correct to pass the quiz. What's the probability of passing the quiz by guessing? Now here is kind of what I was talking about here, where we have a different answer for 15 versus 16 versus 17, a different of it being exactly. So here what we need to do is we need to do just that of working through, well, she could get 6 and pass, she could get 7 and pass, she could get 8, 9, and 10 and still pass. So our job is to do this that many times, and when you can do or more, you add each one of these. So I figure out each one of these individual probabilities, and when I add them all up, then I'll know what's my overall chance of still passing. So she has to get 6 through 10, or any of those, and that'll be correct and work. So what we do is we do each one of these separately. So this is the probability of getting 6 right. Notice there's 10 questions. This is the chance of getting 6 right, and each individual, it's true or false, so you get half chance of getting it right or wrong. And then we do it again for 7, for 8, for 9, and for 10. Okay. And then if we work out those formulas, basically this 0.2051, that came from doing the whole combination of 10, 6 times 0.5 to the 6th power, and then times 0.5 to the 10 minus 6 power. And that is happening for each one of these. So you do it for each individual one, and that'll give you these. So this one is for the 0.2051, and then we would do another one here for this guy, and continue. So this is what you have on one of your problems in your lab, is to do each one of these separately. And then the key here is to add it up. Okay, so now that is your overall probability of passing this quiz. So work out each one of these, get each one of these decimals, and then add them all up, and that'll give you the final probability of getting just by randomly guessing. So her chances of passing by randomly guessing are 37.7%. So not very likely, but it could happen. So again, the key here is when you've got 6 or more or anything like that where you want to figure out multiples, you find the individual probabilities and then add them together to get your overall probability of that overall occurrence happening. Okay. So if you have any clarification questions on any particular questions in the lab, please let me know just through the Ask My Instructor feature.